In this session, I would like to demonstrate the design of both flux reactor as well as the CSTR. And this is the reaction that is happening. It's a gas phase reaction. We expect to find out the volume of the reactor necessary to obtain 60% conversion. So the reaction is irreversible and elementary. That means it is first order. And you are operating the reactor isothermally at 1150 Kelvin and a pressure of 5 bar or 5 atmosphere. And the pure ethane is entering at 1150 Kelvin and 5 atmospheres. In addition to this, you are also given the rate constant 0.072 at 1000 Kelvin and an activation energy equal to 80 kilocalories per gram mole. Now let us try to design this reactor for this particular example using Aspen. So the components that we are handling are only three: ethane, ethylene and hydrogen. So first of all, define these components. Ethane, then ethylene, hydrogen. So after defining the components, go to the next input screen, choose an appropriate property method, go to the next input, choose simulation environment. Now you can see I'll be adding another reactors later, so I'll be using a manipulator, duplicator first, so that we can add another reactor for design. Initially, let me add only a CSTR. So you can see this is a CSTR model, this is the plug flow reactor model. We already saw how to simulate a batch reactor. CSTR. Now let me connect the input and output streams. So once we draw this flow sheet, now let us go into the next input screen. So we were given this data. So let me change it to maybe SI unit system. So the feed is entering at a temperature of 1150 Kelvin and 5 atmospheres. Flow rate, pure ethane is entering at a rate of 1 kilomole per second. Did I miss that statement here? The flow rate of 1 kilomole per second, you can take that. We have defined the input stream. We have to give information with respect to the output stream. Okay. Duplicator, you don't have to specify anything. Now, the specifications of the reactor are, already we said this, it is also operating at the same conditions of 5 atmospheres and 1150 Kelvin isothermally. Now remember, be careful with this phase. We are given that this reaction is a gas phase reaction. So this is one place where you will be able to get the valid phases for the reaction. And in case if you have other things, you can choose, but we are going to calculate the volume of the reactor required to obtain a given conversion. But the problem here is this model is going to operate in rating mode. What do you mean by rating mode? Given the input streams, operating conditions and equipment parameters, we will be able to calculate the output. But we know the output, that means we wanted to get 60% conversion and we are required to calculate the volume. This is not possible in any rating model. So we need to convert this design problem into a rating problem. First of all, by assuming some volume of the reactor. So assuming the volume, we will be able to complete the problem definition required for rating, and we should be able to simulate it, calculate the conversion, compare the conversion with what we require, and then vary the volume in order to get to the required conversion. So it is going to be an iterative process. So we have done this. Next. So we wanted to use a reaction R1. By default it names it as reaction 1. What type? So you can choose the type of kinetic model that you are going to use. We are given that this is first order. So I'll select this as power law model. Okay, next. Now define the stoichiometry. So ethane, the coefficient is 1. This is the exponent to the concentration term of ethane. Because it is first order, I am defining it as 1. And the two products are ethylene, the stoichiometric coefficient is 1, and hydrogen also 1. There are no exponents with respect to the products because this reaction is irreversible. So we have defined the stoichiometry. Still, some more information is required because this red dot should be addressed. Now you can see earlier when we were talking about the reactor, we saw that it is vapor phase. So you need to convert this also into vapor, maintain consistency in the reactor as well as when you are specifying the kinetics. Otherwise, results may not come. I think you can look at this equation. This is your Arrhenius law. What is this n? So if n is equal to 0, k is equal, rate constant is equal to a into e power minus e by RT. Similarly, this is in the integral form. If you know the rate constant at one temperature, you should be in a position to calculate the rate constant at another temperature, even though you don't know the value of a. Right? So, depending on the type of data that you give, it will be taken either, you will be calculating the rate constant either from this equation or from this equation. Be careful about that. By default, n is equal to 0. That means you are going to use Arrhenius law to represent the temperature dependency of the rate constant. But if you want to use collision theory or transition state theory, accordingly, the value of n will change to either half or 1. Okay, so by default, we will be using Arrhenius law. So let me not touch this value of n. Now remember one more thing. You can see this comment. You need to type the pre-exponential factor in SI units only. You were given the value of rate constant as 0.072 second to the power of minus 1, which is in SI units. So you should be able to specify that value 0.072. Remember, whatever value that you give here, if you this value is taken as frequency factor. But we know this value is the rate constant at a temperature of 1000 Kelvin. So the moment you specify this, automatically it will be using this equation. You know the value of K0 at T0. We are going to calculate K at any given temperature using this equation. Now you don't require the value of A. So we need to specify the activation energy, which is given as 82 kilocalories per gram mole, I suppose. Yeah, kilocalories per gram mole. So change the unit system. Required input is complete. We should be in a position to run the problem. We got to our results. Look at the stream summary first. So we said isothermal. We did not assume any pressure drop. Pressure drop is taken to be 0. So you can see the mole flows. So out of 1 kilomole per second of ethane that is entering into the reactor, only 0.62 kilomoles per second is coming out. So what is the conversion? 1 minus 0.62 divided by 1. So it is about 0.3766. That means when we assume the volume of the reactor as 1 cubic meter, we were able to get about 37% conversion. Now in the same way, we should be able to make use of a design spec and calculate what is the volume that is going to be required in order to obtain 60% conversion. Before going into details, let me put you a few questions. This is the advantage of carrying out process simulation. Now let me go to this power law. Remember, when we were conducting this reaction at a temperature of 1150 Kelvin, 5 atmospheres, when the order of the reaction is 1, we were able to get about 37.66 percentage conversion. Now let me change the kinetic information slightly. Now this is first order reaction. Originally it is first order reaction. I would like to check what will happen if, keeping everything else constant, what will happen if I increase the order to 2. So do you expect the conversion to increase or decrease when the order is increased from 1 to 2? You can clearly see or probably analyze. Now once again you can see into the details. Now you can see the mole flows. Out of 1 kilomole per second of ethane that is entering, 90.96 kilomoles is coming out. That means we got only 3.78% conversion. So please verify whether it is as per your fundamental principles or not. In the same way, let me also modify one more time. So originally it was first order. We saw what will happen if you change it to second order. Similarly, what will happen if I change it to something lower, 0.5. So again, check up the results. So you can see we were able to get a conversion of 88% if the reaction was behaving with half order kinetics. First order 37%, second order about 3%, 3.7% or so. So please check whether these results are in accordance with some of your fundamentals or not. In the same way, I'll go back and probably change the reaction back to first order. This is what we want to do, and use a design spec to calculate the volume of the reactor required in order to obtain 60% conversion. So new variable is like what we did earlier, FA0. In fact, we know the value of FA0. Pure ethane is entering, which is 1. So let me save some time. I wanted to see what is the molar flow rate of ethane at the exit of the reactor. So this is a stream variable. It is mole flow. Stream is 3, the exit from the CSTR, and it is with respect to ethane. Now what is the spec? 1. This is the inlet molar flow rate of ethane. The outlet molar flow rate is FA divided by FA0, which is 1. In other words, 1 minus FA is going to indicate the conversion. And what is the conversion we are looking at? 0.6. And specify some tolerance, or even more. Now what is that we are trying to vary? Remember, we got to a conversion of about 37% by converting the design problem into a rating problem and assuming the reactor as 1 cubic meter. So let me vary the volume of the reactor, which is a block variable. There is only, okay, the block B2 is going to represent CSTR, and this is volume. Specified reactor volume, cubic meters. We assume this as 1. With 1 cubic meter, we got only 37% conversion. So the volume of the reactor should be more than 1. So let us assume that it is somewhere between 1 and 10. Now once again, you can see this is what is going to happen. So we started with some volume, which is 1 cubic meter. Calculate the exit flow rate. So 1 minus FA should be equal to 0.6. Compare whether you got that result or not within the tolerable limit. Then if it is not reaching a convergent solution, you go back and readjust the volume, readjust the volume. So this is how the design spec is going to operate. Let us run this problem. Now you can see because of the design spec, this block B2 is iterated maybe 6 times. Again, the method used is secant. We were able to reach a convergent solution. Let us look at these results. So when we assume the value of volume as 1, the outlet flow rate of ethane is 0.62. But when the volume of the reactor is about 2.88, then the outlet flow rate is 0.4. So what is the conversion? 1 minus 0.4, that is equal to 0.6. So we got to our requirement. So the volume of the reactor that gives you the required conversion of 60% is calculated as now 2.8843. Let me go back and see the stream results as well. when the design spec reaches convergence, so it will be replacing the block results as well. So this is the inlet flow rate to the reactor. This is the outlet flow rate. So we got a conversion of 0.5999, right? 0.6. Apart from this, let us also see what other information would be available from the block results. So you can see this is the amount of heat duty. So what is this? This is positive. What do you mean by this? This reaction is endothermic because the reactor is operating at 1150 at a constant temperature of 1150 Kelvin. Unless and otherwise we add this much of heat, it may not be possible for us to keep the temperature constant. So the residence time of the reactor is about 0.05 seconds. So balance. So this is the mass and energy balances. There is a difference in energy balance because we did not address how this required heat is supplied. So reaction kinetics, now you can see rate units, kinetic factor, driving force, reactor volume. Right? So this is how you should be in a position to design the reactors. Now in the same way, we should be able to, let me delete or deactivate this design spec, or probably delete itself. Yeah. So now, in the same way, we should also be able to design a plug flow reactor. So let me also connect this. Now, what would be the volume of the plug flow reactor? So the cross-sectional area is pi by 4 d square and the volume is pi by 4 d square L. So you can think of assuming some length, calculate the diameter that may be required in order to solve this problem. Let me go back. Go to the next input screen. So this is the case of plug flow reactor. So we are going to operate the reactor with specified temperature at constant value of 1150 Kelvin. Remember, the gas phase reaction is being affected by the pressure. Of course, when you say the pressure drop is 0, automatically it will be at 5 bar, whatever is the inlet pressure. Now let us go to the next. So pi by 4 d square L, we need to calculate, right? We wanted to do just 1 second. Let me assume some length and volume. So the roughly let us say the volume of the reactor is equated to about 3 cubic meters. Pi by 4 d square L is equal to 3, right? L is equal to 3. So pi by 4 d square is equal to 1. From that, you should be able to calculate the diameter, right? The diameter comes to, this is nothing but the d square is equal to square root of 4 by pi or 2 by root pi. Try to calculate that value, it will come to about 1.128 meters. So again, here we can see it is vapor phase. Next, reactions. So the same reaction has been already defined in the case of CSTR. I am also using the same reaction even in this plug flow reactor. So I think we have completed all our data. So just 1 second. In order to compare, we assumed this reactor as 1, but we calculated the volume required to obtain 60% conversion as 2.88. Now the volume of the plug flow reactor is taken as 3. So I'll equate the volume of the CSTR also as 3 and try to compare the conversions obtained in both the cases. One thing that you can see here is there are many options which I did not specify. You can use a multi-tubular reactor. So if you decide on the number of tubes, then you need to specify the dimensions of each tube. So the overall volume will be the volume of each tube multiplied by the number of tubes. That way you can handle it. Anyway, we should be able to run this problem. got to our results. You can go back. Now, when you are using 3 cubic meters, probably you may be getting slightly more than 60% conversions. Because 2.88 gave us 60% conversion. Now it is giving us something like 60.8% conversion when the volume of the reactor is 3 cubic meter. This is the case for CSTR. What about PFR? We were using the volume as 3 cubic meters in the case of a PFR. Now what will be this conversion? Will it be more than 60? Less than 60? So you can see we were able to get a conversion of 80.8%. You know, PFR will be better compared to a CSTR for all reaction orders greater than 1. So in the same way, to avoid time, I would like to demonstrate a few more reactors. In fact, you can see, you can do things like this, the same reaction, same kinetics. I'm using a duplicator block. The input is same as what we have considered here. So 1150 Kelvin, 5 atmospheres, the reaction is same and so on. Now what I am trying to do is I have taken number of outputs from this duplicator block, and all these outputs are going to have same information as that of the input. You can see the results of each of these reactors. Here I have a CSTR of 3 cubic meters. Right? We already saw the result in the previous case. So the result here is 60.8% conversion. Right? 1 CSTR of 3 cubic meter volume. Similarly, a single PFR was giving us a conversion of about 80.8. Right? CSTR compared to CSTR, PFR is better. Remember, these two are isothermal. Now, in this case, I am operating the reactor under adiabatic conditions. Same input, but only result is adiabatic. Already we saw that this reaction is endothermic. So what will happen if I conduct this reaction under adiabatic conditions? The outlet temperature will come down and the conversion also comes down. So you can see from 1150, the temperature came down to about 1019 because the reactor was operating adiabatically, wherein you are not supplying the required heat. So the conversion came down from 80.8 to 11.6. The same volume plug flow reactor is employed here in both these cases. Now what I am trying to do is I am conducting this reaction in 2 CSTRs connected in series, each one with 1.5. Right? So when I do this, what will be the conversion that I can expect from these 2 CSTRs? The total volume is similar to the volume of this single CSTR. Now you can see the result of this. So it is supposed to give you more than 60% conversion. I think you might have seen this principle in your reaction engineering course. So 1 CSTR of 3 cubic meter was giving us a conversion of 60.8, whereas 2 reactors of total volume, 2 reactors connected in series of total volume same as 3 cubic meter was giving us almost 69% conversion, better than the conversion obtained in 1 reactor. Now in the same way, I am dealing with this reaction in 2 PFRs, each of 1.5 cubic meters. Now what do you think will be the conversion here? You know already that the conversion will not change in the case of PFRs even though you are operating them in series, like what you saw in the case of CSTR. Please verify some of these principles from your reaction engineering course. Now what I have done is, I have connected 6 CSTRs in series, each of them having a volume of 0.5. So the total volume of all these 6 reactors is similar to the 3 cubic meter volume, equivalent to the volume of 1 CSTR. What do you expect the conversion here to be? So it is going to be better and better. So we got to a conversion of about 76% conversion. Please look at the results. 1 CSTR of 3 cubic meter volume gave us about 60.8% conversion. 2 CSTRs of 1.5 connected in series gave us a conversion of 69%. 6 CSTRs gave us a conversion of about 76% conversion. We already know the theoretical result. As the number of CSTRs connected in series increased to a large number, the performance of this reactor battery we'll be approaching the performance of a PFR. The PFR gave us 80.8. Now these 6 CSTRs gave us a conversion of about 76%. So if you are interested, you can add probably a few more reactors. As you keep on increasing this number, you will be approaching a conversion of 80%. These results are already theoretically available to us. Now what I have done here in these two systems, a CSTR followed by a PFR, PFR followed by CSTR. Remember the kinetics, the input rates, the conditions are exactly similar. Now, which one do you think will give you a better conversion? Do you think the arrangement, which reactor comes first, is it going to affect the performance? In fact, even this probably you might have solved. Let me see the conversion obtained in the case when I am using a CSTR followed by a PFR. This was giving us a conversion of 70, almost 75%. CSTR followed by PFR. Whereas PFR followed by CSTR, let us see the conversion here. Remember, both these reactors are similar, only the order in which they are appearing is different. So PFR followed by CSTR gave us slightly better conversion than CSTR followed by PFR. Even this theoretical result is already known to us. Similarly, what I am trying to do is, remember these two reactors are same. In fact, what I am doing, let me see, 0.5 followed by 2.5. And in the previous case, 2.5 followed by 0.5. The order was different. So don't be under the impression that this is because this is larger. So these two are same, these two are same. Which one is better out of these two arrangements? Again, you know, theoretically, the second system, this system should be able to give you a better conversion than the first one. So, you know, this is giving us a conversion of 65.62%, a small CSTR followed by large CSTR, whereas, large CSTR followed by small CSTR is giving us 65% conversion. Small CSTR followed by large CSTR should give us a better conversion than that. So it is about 66% conversion. So like this, you can simulate many reactor models. So what I am doing here is a PFR, small CSTR, large CSTR, small CSTR, PFR, large CSTR, small CSTR, large CSTR and PFR. Out of these three, which is better, and see whether you are getting the same result as per your theory. So with this background, I would like to stop my presentation. So you are at liberty to use any such combination of reactors, and as long as you are in a position to define the kinetics, you should be able to simulate and design the reactor.